Hi everyone! In this video we are going to review acid-base chemistry. Then we'll talk about how to form something called an alkoxide. And then we'll review a little bit of how to prepare alcohols. So let's look at acid-base chemistry. So when you first started taking chemistry, you probably remember learning about how water can act as an acid or a base. And if water reacts with itself, so let's say one of these is an acid, the other is a base, you end up forming the hydronium ion and the hydroxide ion. So the oxygen on the base will take a hydrogen from the acid and electrons will be left behind. Okay, now notice that the equilibrium arrows that I drew greatly favor the left-hand side of this reaction, so the water molecules. Why is that? So let's look at how acidic water is compared to the hydronium ion, which is our conjugate acid. So that means we need to look up the pKa values. So you might recall that the pKa value of water is 15.7, or around 15 is fine. And then the pKa of the hydronium ion is negative 1.7. So which one is more acidic? So remember, a lower pKa value means a stronger acid, so the hydronium ion is more acidic. So if you have a really strong acid, that means it's very reactive. It really wants to give up a hydrogen, and so the hydronium ion will want to react with the hydroxide ion to reform water. So that's why equilibrium highly favors the water molecules. Okay, so now what if we're working with an alcohol? So here I'm just writing a generic alcohol, and that R group is just an alkyl group. It could be a methyl or an ethyl or tert-butyl, whatever you want it to be over there. And let's say this is reacting with water as well. So water can act as a weak base, and alcohols can act as acids. So again, the oxygen from our weak base will come in and deprotonate the alcohol, and electrons will be left behind on oxygen. So we end up forming something called an alkoxide ion. Oops, that should be a negative charge, not a positive. Negative. And then our other product is, again, the hydronium ion. All right. So you'll notice again that equilibrium greatly favors the left-hand side of this reaction. And again, that has to do with pKa values. So we already said that the pKa value of the hydronium ion is negative 1.7. Well, if we look up pKa values for alcohols, that can range from 9 to 18. So it really just depends on what that R group is. So again, the hydronium ion is going to be very reactive. It's going to give up a hydrogen and form that alcohol and water. Now, why do we have such a wide range of pKa values? So what can impact acidity? So remember, all the way back to 261, we talked about cardio rules. And remember, C stands for charge, which on an alcohol is neutral. A stands for atom, and our alcohols will have the same atoms, O and H. R stands for resonance, and remember when we talked about acid-base chemistry in the past, we said that if something has resonance, that's going to stabilize the molecule, or in this case, stabilize the conjugate base. So resonance can have an impact on acidity. Next, D and I stand for dipole induction. So that's where you might have really electronegative atoms bonded to your molecule, like fluorines or bromine or chlorine, something like that. And those can draw electron density towards themselves and stabilize the conjugate base as well. So that will have an effect on the strength of your acid. So dipole induction is also important there. And then orbitals, we're probably going to have similar orbitals, so we don't have to worry about that too much. Okay, so how do we favor the formation of an alkoxide ion? Because according to this reaction, it's not favored. It doesn't really form to a significant extent. Oops, there we go. So there's a few different ways that you can create an alkoxide. One method involves using a strong base, such as sodium hydride. So the hydride will come in and deprotonate the alcohol, and electrons will be left behind on oxygen. And what would our products be? Well, we'd have our alkoxide ion where the oxygen is negatively charged. And the sodium ion is just there to balance charge, so we could even just add it on here. And what's our other product? H2, which is hydrogen gas. All right. Now, the reason that the products are highly favored here is due to that hydrogen gas. So the hydrogen gas is going to bubble away. And according to Le Chatelier's principle, if you remove product as it forms, then the reaction will favor the products. So the reaction will keep producing more product. So this is how we can favor the formation of our alkoxide ion, because that hydrogen gas, the other product, is evaporating off as the reaction proceeds. Okay, now one question here. How would we name the alcohol that we drew? What's that alcohol called? So it has a 2-carbon chain. So the prefix would be eth. And then if we just had an alkane, this would be called ethane, but we're going to drop the E and add OL for the alcohol. So this is ethanol. And ethanol is found in alcoholic beverages. It's also found in gasoline. So it's in a lot of different liquids. And then to name the alkoxide ion, we would write sodium ethoxide. So instead of ethanol, it becomes ethoxide. Okay, now there is another way to perform this reaction. And this one's kind of cool. This one involves using pure lithium, pure sodium, or pure potassium. And I'm just going to write a little degree symbol or not symbol next to each of those. And that just means that it's a pure metal. So what you would do is get your alcohol, and then you would chop off some pure metal from your metal block, and you'd end up with that same alkoxide ion, although the spectator ion would be different depending on which one you use. So it might be sodium, lithium, or potassium. And then your other product would be half an equivalent of hydrogen gas. So this is actually one way that you can make tert butoxide, which is something that we've used a lot of in elimination reactions. Oops, I was going to draw tert butoxide, but I want to start with the alcohol. So this is tert butanol. And let's say we add pure potassium here. We would end up with potassium tert butoxide. And you don't have to worry about the mechanism for this. This is just, a suggestion for how to make your bulky base. And we'd also have half an equivalent of hydrogen gas. Now remember, tert butoxide is very useful because we can use it to favor the Hofmann product in our elimination reactions. And the Hofmann product is the less substituted alkene. All right, so now let's just review really quickly how to prepare alcohols. And we're just going to go over substitution reactions. And then on the next slide, we'll go over some of the reactions we've learned this quarter. So last quarter, we talked about SN2 and SN1. So we could start with a, oh, my pen stopped working. Hold on. There we go. So we could start with a primary alkyl halide, or we could start with a tertiary alkyl halide. Now, if we're using a primary alkyl halide, which means that the leaving group is bonded to a primary carbon, that can really only go through SN2. Because remember, an SN1 reaction forms a carbocation intermediate, and a primary carbocation is super unstable, so it's very unlikely to form. So this would have to go through SN2. All right, so if we're performing an SN2 reaction, would we use a weak nucleophile or a strong nucleophile? A strong nucleophile, because everything's going to happen in one step, so the nucleophile is going to attack first. So we could use something like sodium hydroxide here to get our alcohol. So that can come in and attack the carbon that's bonded to the leaving group, and then the leaving group heads out, and we get our alcohol. And what type of alcohol is this? Primary, secondary, or tertiary? Primary. All right, now what if we have a tertiary alkyl halide? So the leaving group is bonded to a tertiary carbon. Well, this would have to go through SN1. So unfortunately, with SN1 reactions, you can also have a competing E1 reaction. However, elimination reactions are favored at higher temperatures, so you could try to limit that reaction by decreasing the temperature. But it kind of depends on the reaction you're doing. All right, so for an SN1 reaction, would we want a strong nucleophile or a weak nucleophile? A weak nucleophile, because remember, we're first going to form a carbocation, and then the nucleophile will come in later. So we could use H2O, to get our alcohol. And would this be a primary, secondary, or tertiary alcohol? Tertiary. Okay, so now let's just review some of the reactions that we've learned this quarter so far that will give us an alcohol. So addition reactions will give us an alcohol. So for instance, if we start with this simple alkene, we can use acid catalyzed hydration. We could use our oxymercuration demercuration. Or hydroboration oxidation. All right, so let's take a minute and try to figure out what our products would look like for each of these reactions. So you can pause the video, and when you restart, we'll go over them together. All right, so remember when we're adding something across a double bond, we have the more substituted carbon, and then we also have the less substituted carbon. So if we perform the top reaction there, the acid catalyzed hydration, would the alcohol group add to the more substituted carbon or the less substituted carbon? The more substituted carbon. What about our next reaction, oxymercuration demercuration? Would the alcohol add to the more or less substituted carbon? The more substituted carbon again. Okay, and what about our last reaction, hydroboration oxidation? Does the alcohol add to the more or less substituted carbon? The less substituted carbon. Okay, so the first two reactions give us a Markovnikov addition. And then the last reaction gives us anti-Markovnikov addition. All right. So I think we'll stop there today. Next time, we're going to talk about how to prepare alcohols via reduction reactions. And we're going to need to review oxidation numbers. So we're going to have to think way back to general chemistry. So we'll do that in the next video. I'll see you then.